All right, hey everyone, we're going to look at the mathematics of z-scores today. I think you'll find it to be sort of interesting, and it's going to open up a lot of your thinking as far as things you've seen in your score reports or maybe just in passing, and it's going to help to really build some serious fundamentals that we need for the rest of the year. So let's go ahead and start. One thing that we've been kind of hinting around about, I think it showed up in a homework assignment, is this notion of parameters versus statistics. Here is what we've got. Statistics are things that come from samples. They can be the mean, the standard deviation, median, IQR, just so long as it comes from some kind of a subset of a greater whole. You pick a group of people at random, you start taking measurements, those measurements are considered statistics. Parameters, on the other hand, are similar insofar as the numbers, what we're going to call the numbers and whatnot, but these are going to be values that are actually out there for entire groups or entire populations. So for example, if I need the average weight of an 8-year-old male in the United States. There are a lot of 8-year-old males in the United States, so much more so than I could ever possibly get to in my lifetime. And by the time I was halfway through, some of the 8-year-olds I wouldn't have gotten to would be turned to 9-year-olds, and some of the 7-year-olds that I skipped over behind me turned 8, and it's impossible. So rather than give up that question or give up that quest for knowledge, we're going to do an end around using sampling, and we're going to get values for samples or statistics that we hope will infer back to the population. All right, so parameters are fixed and typically unknowable values that we're interested in from populations. Statistics come from samples, and those statistics are used to estimate the parameters of interest. So when we're dealing with a sample, the notion for mean and standard deviation, or the notation rather, are X bar and S. Okay, we've seen those before. Those are known as statistics. If we're dealing with an entire population, as I just mentioned, the notation for the mean and standard deviation changed to Greek letters. So we typically use, Greek letters for parameters, and we use, regular, Latin letters for statistics. So mu and sigma, mu would be, what we would estimate with X bar, it's the population mean, and S, standard deviation from our sample, would be used to estimate sigma, the true spread in the population. So those values are parameters. Parameters, P for parameter, P for population. Statistics, S for statistics, S for samples. Good way to remember it. And these parameters are usually things we just can't know. But we don't just give up because we can't know them. We find a way. All right, so what about standard deviation? We can use that a lot like we used percentiles, insofar as we use percentiles to kind of measure, like, for example, Q3 is 25% of your data above the mean. So that's sort of like a measuring stick. Here we're going to try to use standard deviation as a ruler or a measuring stick. So the trick in comparing very different looking values is to use standard deviation as rulers. Standard deviation tells us how the whole collection of values varies. It is the most common measure of variation. What we're going to do is we're going to standardize and create z-scores. So here's the process. We can compare individual data values to their mean relative to their standard deviation by using the following formulas. All right, if we're just taking values from a sample, we first get deviations, right? Our value for X, whatever it happens to be, minus the mean of the data set, that'll give you a deviation, divided by the standard deviation of the sample. Or if we're dealing with these idealized unknowns in the population, we're going to use x minus mu for the mean over sigma for the standard deviation. Now, we'll assume when we get numbers for these two things that they'll be true. We call the resulting values standardized values, and they're denoted as z. They can also be called z-scores. That's what I call them. So if I'm using like test score units, and I have a test of 80, and the mean is 70, I do 80 minus 70, and I'd get a difference in test score units divided by the standard deviation of that data set, which is also in test score units, and the units just cancel out. So they're going to end up being in standard deviation units. Same thing over here for the population values. So standardized values have no units. Whatever's in the numerator will also occur in the denominator, and they just cancel out. So they measure the distance of each data value from the mean in standard deviations. Now keep in mind that mathematically distance is usually considered to be a positive value. Not so much here, all right? The distance can be either above the mean or below the mean. So we're going to retain negative values. So a negative z-score tells us that the data value is below the mean, while a positive z-score tells us the data value is above the mean. If I try to standardize a value that's exactly at the mean, then I'm going to get 0. So if your z-score is 0, that's going to be a value that's right there at the mean. So standardized values have been converted from their original units to the standard statistical unit of standard deviations from the mean. So they're in standard deviation units. And so when we do make those conversions, then we can compare values that are measured on different scales with different units or from different populations. So yeah, I mean, if you're measuring the same thing with two different instruments that are scaled differently, you can convert both the z-scores and then they become comparable. I think we'll see that here in a minute. All right, so I'm going to pause this and get out of here. We've still got a little bit of ways to go for rescaling and whatnot, but what I want to do is look at some things that we can do on paper. So this is page 7 in your packet, and we're looking at activity number 3. So suppose that a college admissions office needs to compare the scores of students who take the SAT with those who take the ACT. Now they're scaled completely differently. However, for both of them, they both start with z-scores, and then they add the scaling in later, because I don't think your parents are going to be too appreciative if they pay for an SAT or an ACT score and you get a negative number, or worse yet, a 0. Yeah, so they scale them so you don't see any negatives or zeros. Anyway, suppose that among the college applicants who take the SAT, scores have a mean of 896 and a standard deviation of 174. So let's just go ahead and record that. So SAT, this will be mu. We're going to call this mu because that's for everybody. So that'll be 896, and sigma is going to equal, what did they say, 174? And that's for the SAT. For the ACT, mu is going to be, what did they say, 20.6? And then your standard deviation will be 5.2. So they're really scaled quite differently. So if Bobby scores a 1080 on the SAT, how many points above the SAT mean did he score? So they were just looking for a deviation here. So 1080 minus the mean, which is 896. And the difference here is 184. And this would just be called a deviation. It's not a standard deviation because we haven't adjusted it. So if applicant Kathy scores a 28 on the ACT, how many points above the ACT mean did she score? All right, we'll get her deviation. So 28 minus 20.6, and that should give you 7.4. And again, that's also a deviation. I'm not going to bother writing it again. But even here, this is not a comparable thing if you're in an admissions office. So you need something that is. So I need to get to this next screen, so I'm just going to pause real quick. All right, that was quick. So here's page 8, and the question is it sensible to conclude that since your answer to A is greater than your answer to B, that Bobby outperformed Kathy on the admissions test? And we got to explain it. And I would say that no, you can't compare. You can't compare two test scores that are in a different metric. All right, Bobby is in SAT score units, and Kathy is in ACT score units. So yeah, that's not going to be a good thing. So if we standardize them, then we're going to get these things in standard deviation units, and they should, since SAT and ACT, I guess, are purported to measure mostly the same thing, that we can go ahead then and compare. So let's start with Bobby. And Bobby will just do Z. And remember, that's going to be x minus mu over sigma. So that'll be equal to, let's see, 1080 minus 896. And we'll adjust that by 174. And we'll get a z-score, which will be 1.057. A lot of z-scores are just two places, so 1.06 would be fine. And let's look at Kathy. And Kathy, her score was, well, I'm not going to rewrite the formula here. You can see it with Bobby. That'll be 28 minus 20.6, and that's all over 5.2. And so her z-score will end up being 1.423. So, looks like we got a winner here. Kathy is the winner. So there it is. So what we did was we found a z-score, or standardized, it says so right here. It should only be used when working with mound-shaped distributions. I'm going to clarify that. In fact, people standardize things that aren't necessarily mound-shaped, so we will mostly do that, but you can standardize anything. And actually, these two tests do, their score reports, in summary, cumulatively do exist on a bell-shaped curve. So here's your formula, and remember we can do it with samples, so that could be an X bar and an S. So which applicant had the higher? That was Kathy. She had a higher z-score. And then explain in words which applicant performed better on his or her admissions test. And I'm going to pause and write this out to save you from sitting through watching me writing it out. All right, that was quick. So Kathy performed better because her z-score, and this is important how I'm saying this, her z-score is 1.423 standard deviations above the mean of the ACT, whereas Bobby's score is 1.057 standard deviations above the mean of the SAT. All right, so if you're an admissions officer and you accept either test, then you would have to believe that they both measure the same thing. Now that you've got them in a similar metric, then you can compare. So there it is. So pause this and maybe jot that down, and I'm just going to keep going. So calculate the z-score for Peter, who scored 740 on the SAT, and for applicant Kelly, who scored 19 on the ACT. So let's start out with Peter. And remember, this is going to be z equals x minus mu over sigma, whatever that number is. So Peter is going to be 740 minus 896 divided by 174, and that will give you negative 0.8966. Get that dot to show. And that's for Peter. And for Kelly, she's our ACT person in this question, she scored a 19, so that'll be 19 minus 20.6 over 5.2, and that will be negative 0.3077. All right, so which person has the higher z-score? Now remember that negatives kind of work backwards. If this were positive, it would be Peter, but with Kelly, you're closer to 0 than Peter is, so that'll be Kelly. All right, so if you're comparing those two, we've got a winner with her. So it says, under what conditions does a z-score turn out to be negative? And let me go ahead and pause this so again, you don't have to watch me write it. All right, through the magic of video, there's your answer. When z-scores are negative, that's when an observation in question or that you're working with falls below the mean of the distribution. Ooh, where's my n at the end? Let's put that on there. And that's real simple. And if your z-score turns out to be 0, it's because it's right there at the mean. So you can see this will give you a negative when you subtract, and these two will give you positives when you subtract. So go ahead and pause this and jot that down. And I'm going to go back to the PowerPoint. All right. I didn't mean to go back to the beginning. Let's see if I can get out of here. Escape key. And I really want it to be down here. Okay, let's go here. All right, so this is going to be what happens when we do scale or rescale values. And so we're going to look at shifting data. So here we've got two distributions. They look really similar. So let's read what it says. Shift from men's actual weights to kilograms, right? So above a recommended weight by subtracting 74 kilograms from each. So here is a person's weight. Here is what it is after we subtract 74 from all the individuals over here on the left. And there's some box plots that go along with it. And you can tell that that changes the scaling a little bit insofar as, like, if you pick a center here, let's say a balance point might be here at about 90, but then that changes to whatever it would be 90 minus 74. So you're seeing a shift of this distribution over to the left, all right? But really the spread didn't change. It didn't lose its shape, it didn't lose its spread, but it did get recentered, so to speak. So your mean, your median changed, standard deviation, IQR stayed the same. So your point estimate values are going to change. You're going to lose 74 from each of them. But your standard deviation and your IQR are going to stay the same. Measures of spread are not affected by adding or subtracting a value to all the things in your data set. All right, now the values for IQR, like the Q1 and the Q3, those will change, but the actual difference won't. So if you have a measure of spread, it's not going to be changed by a change in centering, like it was happening here. But if you have a point estimate, like mean or median, that will shift either left or right, depending if you're adding a value or subtracting. All right, well, what about if we apply something multiplicative? All right, you're not going to see any horizontal shifting unless that's included, but if you're only multiplying all the values in a data set, you're going to end up with a dilation. Okay, I think it'll dilate every number except 0, because 0 times something is just 0. So what if we change from kilograms to pounds, because aren't there 2.2 kilograms per pound? Well, that's going to create kind of a stretch, right? And look at how that affects the spread. All right, this is real compact. This is a lot more variable. It did change the mean. Let's just say the mean here is, oh, I don't know, 80 for a balance point. Here, it's going to be more like, I don't know, 178 or something like that. So multiplying will change your point estimates, and it will change your spread estimates. So center and spread changed by rescaling. Okay? Rescaling is applying a multiplier, and shifting is just applying an additive constant to all of your data values. All right? So here's a good example. And this one you probably ought to write down. So pause when we're done. Make sure you get it. A unit circle drill in pre-cal was given with a maximum score of 33. The teacher decides to change the scale of the score using this formula. 1.5 times the current score, that's a rescaling. Plus 50, that's a shifting, and that'll give you your new score. So how are these summary numbers changed? Okay, your mean is a point estimate, okay? It's going to change from both the rescaling and the shifting. See, it's going to be 1.5 times the original mean of 27.45, and that's going to change that, and then you add 50 and it'll change it more. So it changes from 27.45 to 91.175, okay? So point estimates are affected both by shifting and rescaling. Now standard deviation is only affected by the multiplicative part, the rescaling. Because if you take, a value and add a constant, add it to all of your data values, it's just going to move them left or right. If you add a negative, it would move it left. All right, so that's going to change, but it's not going to change the spread. It will. Let me back that up. If you have standard deviation or a measure of spread, it'll only be affected by the dilation, because adding a constant will just move things right or left. It won't change the spread, but the multiplier will. Hopefully I've salvaged that. Good save, Garner. All right, the median is a point estimate, so again, it's affected by both rescaling and by shifting. IQR is a measure of spread, so it's only going to be affected by the rescaling. And the maximum is a point estimate. It's a single value. So it's going to be affected by the dilation or the rescaling and by the shifting. So jot those down. All the point estimates will be affected by the multiplier and the additive constant, but the measures of spread will only be affected by the multiplier. Okay, so when you want to think about z-scores, when you standardize data into z-scores, they shift by subtracting the mean, okay, that's a shift, and they rescale by dividing by their standard deviation. Right? Dividing is just multiplying by the reciprocal, and subtracting is just adding the opposite. So you're getting shifts and rescaling with those formulas. So standardizing into z-scores does not change the shape of the distribution. Okay? If it's skewed in one direction or if it's mound-shaped, it'll stay that way. Standardizing into z-scores changes the center by making the mean 0. So that's why you have to do all those tricks with SAT and ACT, because if you got a 0 on your score report, you'd think you were a complete loser when in fact you're right at the median or the mean. It's the same because you're in a bell-shaped curve, and that means 50% are below you and you did better than them, but 50% are also above you. But it's not 0. Standardizing into z-scores changes the spread by making the standard deviation 1. Okay? So we're going to see this especially when we go into normal curves, but it works for any curve. All right, so adding z-scores, I mean, since they don't have a metric, you can so long as it makes sense. So here's a Spanish exam, and here's the traditional mean and standard deviation. They're in the Greek letters, so that's for all the ones that have ever been taken. Megan scores a 77 on the French test, a 95 on the Spanish. Anna has an 83 and an 83. So who does better overall? Well, we got to standardize both and then add them together for each student and then compare. All right, so here is Megan's z-scores, and she got a negative on one. Whoops. And add that to a positive, that's what she got. Anna, who had 83 on both, she was 4 standard deviations above the mean for the one test, and then 0.4 and 0.6 on the other. That adds up to 1. Anna did better overall. All right, we're done. So there's your homework. I even put the page number here so that you won't have to, kind of bounce around in the book to find it. 13 to 25 odd, and then we will move on to new ground tomorrow. So on that note, I'm going to sign off and wish you a good day.